Hello everyone, my name is Atticus Joe, the account manager for the German-speaking region. In this video, I will present to you the book Molding Simulation, Theory and Practice. First of all, I will talk about the motive behind the creation of this book, and then I will walk you through each chapter with concise explanations. With decades of experience in plastic injection molding simulation, we, Moldex 3D, know how important education knowledge are to get to the most out of the simulation software. As a leading provider of plastic simulation solutions, we would like to prepare practitioners and academics from all areas of the plastic industry with knowledge and skills needed to succeed in today's competitive manufacturing environment. In the very first chapter, we're placing the focus on two things. One is the system of injection molding, namely the cycle of injection molding and components of the molding machine, as well as common defects in injection molded parts. The other thing is the core values in molding simulation. To put it in other words, in this section, we will explain why simulation should be the fundamental part of the manufacturing process. The second chapter, we're diving deep into the material properties of plastics, such as rheological, thermal, kinetic, and mechanical properties. The understanding of these properties is essential to obtain the suitable molding parameters, precision of CAE simulation, and most importantly, a desirable product quality. In the third chapter, part and mold design are the leading actors. We put the emphasis on the integration of design guidelines with molding analysis. Whether it should be mold design or part design, there are differing considerations which have to be taken into account. And that's why we'd like our readers to get familiarized with the relevant theories and mechanisms. Chapter 4, Process Conditions. Well, this chapter is divided into 5 sections. The first section gives the main step and item of a molding cycle, and the rest of the sections are written to make further explanations such as plasticizing stage, filling, packing, and lastly, cooling stage. Readers know from the previous chapters that the quality of molded product depends basically on material properties, mold and part design, and process conditions. That's why in Chapter 5, Molding Simulation Methodology, we will discuss how to verify and optimize part design, as well as how to optimize molding process with CAE tools. Also, we will introduce numerical methods, the brief history of molding simulation, and its crucial workflow. In a complete cycle of injection molding, the filling stage determines the whole framework of the molding. Unsuitable process or designs lead to poor product quality, whereas the flow behavior of the material during the filling process directly have influence on all kinds of defects in the part. So in Chapter 6, we shift our attention to the relation between flow considerations and part features, including the introduction of flowing behavior inside the cavity, effects of the filling time, and effects of the part thickness, as well as how the flow rate can affect injection pressure, and many more. The runner system is a transferring mechanism for spreading the melt into the cavity. The design of the runner system determines the functionality, manufacturability, and also economy of injection molded part. In this chapter, readers will be given knowledge about the rudimentary design guide of runners and gates, as well as actual cases on how to use CAE tools to verify the runner systems. In Chapter A, we will discuss the cooling stage. We will introduce heat transfer mechanisms, the effect the mold temperature has on part quality, the cooling channel designs, the relation between cooling efficiency and cooling flow, method of the cooling time estimation. Then, in the section of actual cases, you will be shared with the knowledge on how to optimize and verify cooling design for a digital camera cover and a cartridge. Warpage is a critical quality issue in injection molded parts. It occurs when there is an uneven distribution of shrinkage throughout the product. In this chapter, causes for warpage, are introduced first, then it will come to the methods to resolve the issue, and lastly, a practical example is introduced for better understanding on how to use different molding conditions or utilize molding analysis to predict and prevent future possible warpage. Over the last 30 years, fiber-reinforced thermoplastics have increasingly replaced steel-made automotive components as the high-performance engineering materials for structural application. In this chapter, readers will have a closer look at the basic mechanical properties of fiber, as well as the process principle, theory models, and the advantages and challenges of fiber-reinforced thermoplastics. Next, the practical applications will demonstrate the CAE's capabilities to predict the experiment value in an accurate and realistic fashion. When deciding to apply a hot runner system, practitioners need to consider whether the heating is uniform across all regions in the hot runner system, and whether the temperature control of the heater is precise. Also, the impact of the heat dissipation from the hot runner to mold base on the part appearance, and so many more. This chapter, Hot Runner Optimization, will put the emphasis on the simulation techniques of hot runner molds and their industrial applications, along with the sharing of actual successful case studies. In Chapter 12, readers will be offered knowledge regarding process principle of bi- and co-injection, their own benefits and limitations, as well as presentation of actual cases to demonstrate the CAE's capabilities. Gas-assisted injection molding is a revolutionary molding technology developed to overcome some inherent weaknesses of conventional injection molding. Well, by extending the concept of gas injection molding, the gas is replaced with water as the injection fluid. Well, the concept of water-assisted injection molding has therefore come into existence. As tradition, process principle of the two, their own advantages and limitations, cases of CAE verifications are demonstrated in this chapter. Microcellular injection molding is to enhance the product structure strength using less plastic material with the application of the foaming technique. First, the chapter introduces the fundamental process principle, benefits and challenges, and theory models of this injection technique. Second, two cases of microcellular injection molding and chemical foaming are demonstrated to showcase CAE software capabilities in verification. Well, in this chapter, the powder injection molding, PIN, is introduced. Well, PIN is a fairly young injection technique which can realize parts with complex exterior that are otherwise highly difficult to produce, and thus significantly widens the application scope of powder metallurgy. The highlight of this chapter is about the process principle, the advantages and challenges, and theory models. Next, in the section of practical applications, there are elaborate texts on how to resolve the black line issue in PIN with CAE software. In this chapter, we introduce the Resin transfer molding, RTN. First, the basic principle, benefits and challenges, and its theoretical model are described, and then the real case of a wind turbine blade demonstrates the use of CAE software in assisting the innovative process development. As the size of an integrated circuit component made with wafers is small, the packaging is required to avoid any physical and chemical damages during molding process. In the last chapter of this book, chapter 17, the reader will get acquainted with different types of molding process, their advantages and challenges, the theoretical model, as well as 3 actual CAE cases about wire sweep paddle shift analysis and the warpage prediction. And this concludes my introduction of the book. If you're interested in purchasing the book, the link will be put in the description box. Thank you for your watching.